Everybody, okay. Exam 3 practice. So you'll have 2 hours to do it. To do the exam 3. Okay, the first question. Are the following equivalence relations? So typically to show something's not an equivalence relation, you only need to show it fails one of the 3 things. But here I'm asking for you to list off all the conditions it fails. And if it is an equivalence relation, then what are the distinct equivalence classes? But there's no proof needed. So this first one, for example, is not an equivalence relation. And so why is that? Well, reflexivity, it fails. Oops. Because X is not going to be less than itself, right? That's not a thing. Symmetry, it fails. For example, 1 could be less than 2, but 2 is not less than 1. Transitivity is fine. So again, you wouldn't have to show all of this. But this is sort of like a sanity check thing, or like I'm just showing all the, I don't know, all the reasoning behind it or something. I don't know. Whoops. But feel free to just follow instructions. Oops. Lock my screen. There we go. Okay. So fails. Reflexivity. And symmetry. Boom, roasted. Define a relation twiddle on R as X twiddles R if and only if Y equals KX for some non-zero K. Okay, that's an important part of this. So it turns out that this is an equivalence relation. So for the reflexive thing, you can just let K be 1. Right? So that's fine. For the symmetry thing, if X twiddles Y, then there exists some K such that this is true, and K is non-zero. So since K is not 0, and we're in the reals, right? Then we can divide both sides by K, so we get 1 over K times Y equals X. So Y totals X. Cool. And then transitivity is true because, X twiddles Y and Y twiddles Z. Then we could write Y as KX, and we could write Z as maybe LY, right? For L and K non-zero real numbers. So Z equals, Z equals K times L times X, which is a non-zero real number. Yes, it is an equivalence relation. Yay. Okay, so then what are the relationships? Well, as we saw, right, you could take, so like, let's say you have 2 generic real numbers, say A and B. You could rewrite A as A divided by B times B for B not 0, right? And that's for any B and A not 0. Okay, because A also can't be 0, because remember our K cannot be 0. But 0 can be written as K times 0 for any K, right? Because anything times 0 is going to be 0. So our 2 equivalence classes are going to be 0, which only contains itself, and maybe 1. I don't know, pick your favorite non-zero real number, because every number is going to twiddle everybody else besides 0. Okay. All right. X squared minus Y squared is odd. This is not an equivalence relation because it's not even reflexive. So 0 minus 0 even. Symmetry is fine because X squared minus Y squared even. Then Y squared minus X squared is going to be even again. Transitivity is not the case because if you have like odd, so you need like odd minus even or vice versa, right? Even minus odd to get even. But then you would need, so like this is your X squared, this is your Y squared, this is your Y squared, this is your Z squared, right? Then X squared minus Z squared is going to be even because it's going to be odd minus odd. And not, again, once again, you're not expected to write a whole proof. Okay, so not an equivalence relation. So I know I'm running out of room, but you wouldn't need to write all this stuff. Okay, so not an equivalence relation fails reflexivity and transitivity. Okay. And usually when you show something's not an equivalence relation, you only need to show it fails one of these three things. Okay. Okay, so integers that are greater than 1, x totals y if the GCD of x and y is not 1. Okay, well, reflexivity, this is true because like GCD of x comma x is going to be x, or the absolute value of x, but here our x is greater than 1, so you don't need to worry about that. So boom, because x is greater than 1, so it's not going to be 1. Symmetry, GCD of x, y is the same as the GCD of yx. So that's good. Transitivity, well, this is where things start to go south. You can have GCD of 2, 6, right? That's going to be 2. That's not 1. And GCD of 6, 3. That's 3, which isn't 1. But GCD, oh, I'm running out of room. GCD of 2, 3 is 1. Womp womp. So not an equivalence relation. Fails transitivity. Okay, last but not least, this is the one from your homework. And again, you don't need to prove it here, although you did on your homework, you did have to prove it on your homework, but you don't need to prove it here. This is an equivalence relation. So what's the gist of it? Well, x squared is going to be equal to x squared. X squared equals y squared implies that y squared equals x squared. Well, sorry, equivalence. Right, mod 5, mod 5. So some people use the fact that the 3 lines, you know, that like mod arithmetic via mod is an equivalence relation itself. We were kind of trying to prove that, and we used like division lemma and stuff to prove that. Anyway, so if x squared is equivalent to y squared, is equivalent to z squared mod 5, then x squared equivalent to z squared mod 5. Again, this is not a proof whatsoever. This is just sort of the idea of what's going on. So yes, an equivalence relation. And then here's where stuff starts to get sticky, right? So who do we need to look at? We need to look at 0 squared is just 0. 1 squared is 1. 2 squared is 4. Okay, I'm gonna erase all this stuff now because I need more room. But again, you didn't need to write all of that anyway for this. I probably didn't need to write it either because y'all probably believe me that that's an equivalence relation. I mean, you proved it on your last homework, so. Okay, so 0 squared, 1 squared, 2 squared. I should really make these 3 lines and talk about mod 5. Mod 5, mod 5. Who's next? 3 squared is 9, which mod 5 is 4. And then last but not least is 4 which squared, which is 16, which mod 5 is 1. Okay, so who twiddles each other? Well, 0 is the only one that squared gives us 0. 1 and 4 are the 2 options that square to 1. So here in 0 we have just all integers that are 0 mod 5. Here we have all integers that are 1 mod 5 or 4 mod 5. And then in our last one, we have all integers that are 2 or 3 mod 5. Okay. All right, so give an example of relation on the naturals, which is reflexive, transitive, and not symmetric. How about x twiddles y if x is less than or equal to y? Right, this is, and again, you don't need to prove it, but here we go, right? So x is always less than or equal to itself because it's equal to itself, right? If x is less than or equal to y and y is less than or equal to z, then x is less than or equal to z. Okay, so transitive. And then it fails symmetry because, for example, 1 is less than or equal to 2, but 2 is not less than or equal to 1. So here's my relation. It's not an equivalence relation, but it's a relation on the naturals. Okay. All right. So state the definition of a partition of a non-empty set X. Okay. So let's see, the collection of sets, say X sub I, where I is just, ranging over whatever. Maybe it's just a single number, right? Maybe it's just X in there. Maybe it's ranging over the real numbers because we're partitioning the real numbers and every single element gets its own set, X sub I, okay? Or maybe it's ranging over the natural numbers, I don't know. Is a partition of X if first I need all the xi's to be non-empty, okay, for all I. Second, I need xi intersect xj to be empty when I and j are not the same. Okay, this is an important part here. Okay, if you just say this, well, that's not true when xi equals xj, right? When I equals j. When I equals j, then their intersection is xi, right? So that's an important piece to remember there. And then last but not least, the union over all i's of the xi's has to be the whole set. Okay. All right, so give 3 distinct partitions of the integers. So I want 3 different examples of a partition of the integers. Okay, maybe I do evens and odds. 2x plus 1. maybe I do 0 positives and negatives. I could just do the integers. How about I do like x and the integers such that x is 0 mod 3, x and the integers such that x is 1 mod 3. Well, there we go. X and the integers such that x is 2 mod 3. Okay, here's 3 examples. You come up with a whole bunch of other ones. I mean, you could just say the integers, right? You could say xi I in the integers such that xi is defined to just be the integer I. What else could you do? You could do some sort of combination of these things, like you could do the positive evens, negative evens, 0, and then all the odds. Right? All right. Anyway. So for each x there, what y gives x times y is equivalent to 1 mod 7. So for 1, when x equals 1, well, we just need 1 times 1 equals 1. So y equals 1. Okay. When x is 2, 2 times what would give me 1 mod 7? Well, 8 is 1 mod 7, so 2 times 4 equal, well, let's do equivalence. I should have done that up here too, sorry. So y equals 4. 3 when x equals 3. And on the exam, I'm gonna have it more like fill in the blank, so you don't have to do all this writing out stuff. But 3 times what would give me 1 mod 7? Well, 14 is 0 mod 7, so 15. So we would do this 15, 1 mod 7. So y would equal 5. 4 by number 2, y equals 2, right? Because it's just going to be 4 times 2. Okay. For 5 by number 3, y equals 3. And then last but not least, when x equals 6, well, 6 times 6 is 36, and 35 is 0 mod 7, so woohoo. Okay. For any a, b, and the integers minus 0, is it always true that LCM times GCD is absolute value? So the answer is yes. And so they said, if yes, or I said, they said, if yes, give an example where the GCD of A and B is not 1. So GCD of 2 and 4 is 2, right? Because greatest common divisor. And the LCM of 2 and 4 is 4. So 2 times 4, well, sure enough, that does equal the absolute value of 2 times 4. Okay. So A is 2 and B is 4 or something. Draw 3 non-isomorphic, meaning distinct trees. Draw 2 non-isomorphic, meaning distinct graphs, which are not trees. So it's gonna be good to label, right? So trees, maybe number 1, I have just a dot. I'm gonna draw more than 3. I could have this one, which really looks like a tree. What else can I have? I can have the one that looks like a root system. Just need to be careful that I didn't accidentally make those isomorphic. I did not. I said a lot more, and now I'm already running out of ideas. Oh, I can do like the little starburst, sunburst thing. But remember, trees don't have cycles, so you can't make a loop-de-loop going along only one edge once. Like, okay, so that didn't make any sense. Non-trees. So one would be a point with a loop. Right, that's not a tree because you can go around this. You can start here and then go around it and end back at the spot that you started, so it has a cycle. You can't have something like this, right? You could start here, go down, go back up. That's a cycle. And trees don't have cycles. What else could you have? You could have something more complex. Maybe something like that. How about that? Maybe you start here, you go here, up and down. But that's not the only cycle that's in that. There's other cycles as well. But yeah, so you just don't want anything that has a cycle in it. Okay. Something that you can trace around. Oh, how about the hourglass? That's another sort of famous one. Okay. So say you start here, you can go down, over, up, over. Okay. I started and ended at the same point. I didn't repeat any edges, and so that means that this is a cycle. Okay. So that means it's not a tree because it has a cycle, so it's not a tree. Okay, draw a graph with 3 edges and 4 vertices where the degrees of the vertices are 1, 1, 2, and 2. Okay. There are at least 3 ways to do this, so I'm going to draw 3 ways. So you can go like this. That has 4 edges. I'm sorry, that has 4 vertices, 3 edges, and this edge, this vertex has degree 1. This one also has degree 1, and then these 2 have degree 2. Okay. Number 2, you could have something like this that has 3 edges. You could also have something like this. Because don't forget, loops like this count as 2. So the idea that I often give people is like, you imagine that you zoom in on some vertex, right? So and you just look at how many edges, how many times an edge touches it. Right, so if it gets touched twice, then it has degree 2. If it gets touched once, it's degree 1. If it never gets touched, it's degree 0. If it gets touched n times, then it's degree n. Right, so if you zoom in on a loop-de-loop, you see that it gets touched twice. All right, define a relation such that x equals y if and only if 4 divides x plus 3y. All right, let's get started. We're going to prove that this is an equivalence relation and describe the distinct equivalence classes. So let's start with reflexivity. So let x be some integer. Then x plus 3x equals 4x. And 4 divides 4x, kind of by definition, because x is an integer. So x twiddles itself for all integers. X. Yay. Okay, symmetry. Assume x twiddles y. Then 4 divides x plus 3y. Okay. So, here's where I would go into mod stuff. So if 4 divides x plus 3y, then x plus 3y is 0 mod 4. Okay. Well, there's lots of directions I could go with this. Maybe I minus the 3y onto the other side, so I get x equals negative 3y, but I can add 4y to that. Remember, 4y here is 0. So I add 4y to that, I get y. So it's whenever x is equivalent to y mod 4. Okay, that's when you twiddle each other. That's going to be helpful when we do our equivalence classes. Okay, so maybe I star this or something. Okay, but how does that help us right here, right now? Well, I could minus x onto the other side. So I could say then 0 is equivalent to y minus x. But I can add 4x to that, right? But if I add 4x to that, I get y plus 3x. So y plus 3x is 0 mod 4. Therefore, 4 divides y plus 3x. So y twiddles x. Is that the right direction? X twiddles y, x plus 3y. Yeah, so y twiddles x. Great. Yeehaw. And notice I already said symmetry, so I get to just do a little check. Okay, I don't have to say therefore it's symmetric, right, or anything like that. Transitive. Assume x twiddles y and y twiddles z. Well, I could use this argument with the star above and say, well, that means that x is equivalent to y mod 4 and y is equivalent to z mod 4. But let me show you a different way that you could go about these. And you could have done this something similar with the last one. I believe, at least with the symmetry thing. You can say there exists some k and l in the integers such that x plus 3y equals 4k and y plus 3z equals 4 times l. I add those two equations together and I get x plus 4y plus 3z equals 4 times k plus l. I minus the 4y onto the other side and I get x plus 3z equals 4 times k plus l minus y. But this whole thing is adding and subtracting integers, so it is an integer itself. Therefore, 4 divides x plus 3z by definition of division. So X twiddles Z, so we're transitive. Still need to say my conclusion. Therefore, twiddle is an equivalence relation. Yay. Okay, so now I go back and I say, well, remember this thing that I solved above? X twiddles Y if X is equivalent to Y mod 4. Okay, so if and only if X is equivalent to Y mod 4. So what are our classes? Our classes are 0, 1, 2, and 3. Yay. Because those are our three options, right? If you're 0 mod 4, you twiddle all other 0 mod 4 integers. If you're 1 mod 4, 2 mod 4, 3 mod 4. Okay. All right, so let X, Y be in the integers. Prove using the division lemma. Additionally, you can use modular multiplication that if Y is equivalent to 4 mod 6, then X times Y is not 1 mod 6. Okay. Let's see. So by division lemma, I don't know. There's a bunch of different ways you could say this, but I'm just going to say it kind of like how the division lemma is written. For any X in the integers, there exists unique Q and R in the integers such that X equals 6Q plus R for 0 less than equal to R less than 6. So X is equivalent to R mod 6 for a unique R. You don't have to say that last part, but that's kind of the point here, right? Is that there's only going to be one a unique thing that is. So this gives us 6 cases. Using modular multiplication. Okay, so if X is equivalent to 0 mod 6, then X times Y is also 0 mod 6, right? Because modular multiplication lets us just multiply those two numbers in the integers and then move over to mod land. Okay. X, when X is 1 mod 6, then X times Y is equivalent to 4 mod 6. When X is equivalent to 2 mod 6, this is our first interesting one, then X times Y, well, 2 times 4 is going to be 8. And so that's 2 mod 6. 3, when X is 3 mod 6, X times Y. 3 times 4 is 12, which is 0 mod 6. 4. Well, we get 4 times 4, which is 16, which is 4 mod 6. 5. 5 times 4 is 20, which is 2 mod 6. Okay. Or how about I'll say these are all possibilities. Therefore, there exists no x in the integers such that x times y is equivalent to 1 mod 6 when y is equivalent to 4 mod 6. And I'm just realizing now I should have said that at the beginning. I should have said something like assume or let y to be equivalent to 4 mod 6. So I apologize. I should have said that somewhere above. But yeah. Whew. My hand is tired after that one. Okay, so Euclidean algorithm. So I do realize that this is in like the proof section, but I don't really mean it as like, oh, you write PF and you do stuff. It's more just like, I want you to show me using the Euclidean algorithm what the GCD is. Okay, so what do I start with? So I want 81 and 57. So I would start with my bigger one on the left-hand side. Okay, because a bigger thing is never going to divide into a smaller thing, right? Okay, so 57 only goes into 81 one time. And then plus what? So 3, 4, 24. And so I shift my characters over. So 57 equals 24. Well, 24 goes into 57 twice, because that should be 48, right? 48 plus 9 is what should get us to 57. Shift everybody over. 24 equals 9 times what? 2, because that's 18. So that's plus 6. Okay, shift everybody over. 9 equals 6 times 1 plus 3. Shift everybody over. Oh, we got to our magic number. Okay, so once you have this plus 0, that's when you know that this is our GCD. So GCD of 81 and 57 is 3. Woo. Okay. So I don't know. To me, this is you proving what the GCD is by using the Euclidean algorithm. Okay. Last but certainly not least is Euclid's lemma. Sorry, I almost said algorithm again. So this one, I always like to start with so let P be prime. If you're prime, you must be an integer, so that's fine. Such that P divides A times B for A, B, and the integers. Okay, for some, maybe it's probably better English to say. For some A and B and the integers. Okay. Excuse me. So, all right. If P divides A, then we are done. Right? Because I only needed to show that P divides A or P divides B. So if P divides A, then we're good. Right? If P does not divide A, well, then we really have to show that P divides B, that P must divide B. Well, if P doesn't divide A, then the GCD of P and A has to be 1. Because remember, the only divisors of P are 1 in itself. The only positive divisors, I should say, are 1 in itself. And so if P doesn't divide A, then P is not the GCD of P and A. Okay, it has to be 1. Because they have no common, their only common divisor is 1. And so that's their greatest common divisor. Their only positive common divisor. Okay. So now we get to use Bezout's lemma. Sorry, I'm sure I'm not saying that name correctly. I deeply apologize. By Bezout's lemma, there exists some s and t in the integers such that the GCD of P and A is equal to SP plus TA. Okay, remember this is just one, so 1 equals SP plus TA. My plus looks too much like a T. I really should use a different letter, but here we are. So what is it that I want? I want to show that P divides B, right? If P divides B, then that means that B equals P times some integer, right? And I have a 1 equals blah, blah, blah. So why don't I turn that into a B equals blah, blah, blah. So let's multiply by B. So I get B equals SPB plus TAB. Okay, let's recall what I want. So I want B equals P times, let's say K, for some K in the integers. Well, I have a P here. But this is divisible by P, so I also secretly have a P there. Okay, so let's do that. So since P divides AB, then there exists some, I don't know, maybe L in the integers, such that AB equals P times L. So B equals P SB plus TL. Okay, but this whole thing is in the integers. So P divides B by definition. Therefore, if P divides AB, then P divides A, or P divides B. And so another thing I want to remind you of is in this first scenario with this if P divides A, we're not saying that P can't divide B. It could be that P divides A and B. Maybe A is P and B is P, so it's P divides P squared, and P divides P and P divides P, right? And that's it.